everyone. My name is Henry Wu from Broadcom CSG. So today I'm going to talk about Jericho3 AI Ethernet fabric. So in Mohan's session, he mentioned there are two scheduled fabric solutions from Broadcom. One is switch-based, the other is endpoint-based. So I'm going to talk about the switch-based solution. Okay, so how it looks. This is an example about the switch-based scheduled fabric looks like. So the bottom line is the GPU, and there's a leaf and spine, very typical fat tree topology. And the GPU, the connectivity between the leaf and GPU is a standard Ethernet. It can be 400 gig today and 800 gig tomorrow. And basically, all the intelligence is reside on the leaf device. The leaf device is based on the Jericho family. It's going to do the switch, lookup, queuing, and scheduling. And the spine device is based on Ramon family. So the spine device, basically, it is very power efficient and optimized for the AI workload. Why? Because there's no packet processing in the spine device. It's just, you can imagine it as the hardware to interconnect different leaf devices. And why we call it a scheduled fabric? The reason is because everything is fully scheduled by the receiver. So basically, the traffic will not be able to enter this fabric unless it is explicitly permitted by the receiver. So for example, there are 10 senders sending traffic into this fabric, and they are not be able to get into the fabric until the receiver gets clear credits sent to the sender. Therefore, the traffic can cross over the fabric. So that by that way, we can guarantee that there's no congestion inside the fabric. So the fabric in between the leaf and spine is fully congestion-free. There's no flow collision, there's no congestion. And it gives you a multiple type of flexibility on how to place it. So you can either put together the leaf device in the same rack with the GPU or endpoint. So the distance is very short, a few meters. Basically, you can use the DAC DAC to save a lot of power and cost. On the other hand, maybe there's some condition restrictions in the customer data center. They may need to put together the leaf and spine in the networking rack. Therefore, they will use the long-distance optics to interconnect the leaf with the GPU cluster. So no matter which kind of placement, the behavior is always the same. So it's always receiver-based scheduler fabric, and there's no congestion inside the fabric. So what is the building block about the scheduled fabric? So there are two basic building blocks. The leaf is based on Jericho family, and the spine is based on Ramon family. So what we have in the commercially massive deployment is the J2C plus and the Ramon family. So the leaf, as you can see, the leaf, there are two types of front panel. The blue colored front panel is the Ethernet interface to connect with endpoint. And the red color front panel is a networking port to connect with the spine devices. So with the latest J2C plus and the Ramon generation, you can easily scale out the network to a 18K 400 gig network. And we are sampling the latest Jericho3 AI device and the Ramon 3 fabric. So with the latest generation, you can scale out the network from 18K to 32K, and the port speed from 400 gig to 800 gig. So basically, the Jericho3, this device, actually I bring a sample. So let's take a look at what the Jericho3 AI looks like. This is the latest generation of the Jericho3 AI device. This is a purpose-built device optimized for the AI workload. So it is a 5-nanometer device. You can see this is very big. This is probably one of the best switch silicon you can build by the industry at this moment. And all is 100 gig SerDes. And there's a lot of optimizations for the AI workload. For example, the power has been optimized. Compared with previous generation, there are 40% power reduction. And the latency. And also the pipeline has been fully optimized for the AI workload as well. So we sampled this device early this year, and a lot of customer has been pilot running this type of architecture, and we expect the massive shipment within this year. Okay, we talked about how the fabric looks like and what is the building blocks. Now let's talk about what kind of innovation we have been made in order to make it suitable for the AI workload. There are two attributes. The number one is about perfect load balancing. So in this architecture, there's no hashing, there's no ECMP. So we always guarantee that every flow is taking advantage of every potential data passes. So basically, we will segment each flow into multiple segments, into multiple cells, and equally spread the cell over the potential passes. By this way, we can guarantee that there's always consistent high performance across the links. Second is about congestion-free mechanism. So this architecture handles all the congestion-free and the complexity by the hardware. You don't need to run a very complex congestion mechanism. It always ends up with end-by-end scheduling, receiver-based scheduling. Therefore, there's no collision, there's no congestion inside the fabric. The third one is about zero impact failover. Instead of depending on the software, this is a purely hardware-based solution. So the hardware will be able to detect, isolate, and recover any kind of link failure. And the performance is a multiple order of magnitude better than alternative solution. So for example, we can achieve sub 10 nanosecond convergence speed in case there's any kind of link failure. Because the speed is so quick, so it has the minimum impact to the job completion time. And the fourth bullet is about the radix. We must have a solution which is very scalable and to fit the demand for a larger cluster. So this solution enables you to scale up the network to 32K 800 gig. And you can scale to any size by just putting another layer. So all of them work together and make sure this scheduled fabric works in the highest performance under load and scale, and native support for the multi-tenant cloud application. So let's talk about the attributes one by one. Perfect load balancing. So compared with the traditional data center traffic pattern, AI workload has some significant reduction in the number of flow and a much lower level of entropy. So most of the traffic will be elephant flow, meaning long-lasting and high bandwidth flow. The prevalence of the elephant flow may introduce several issues, including hashing polarization and also the unfairness among the different passes when we are using the traditional ECMP or hashing mechanism. So in this architecture, we root fix all of these issues. How we do it? This is an example. So there are GPU A is sending traffic to GPU B, and at the same time, so the other GPU is sending traffic towards the network in the same time and to the same ingress leaf device. So compared with the traditional hashing mechanism, which just pick up one of the paths for each flow based on the hashing result, this architecture, as you can see, every flow has been fully segmented into 4 cells and equally distributes all the 4 cells by 4 different passes. When they arrive the Ramon, the spine device, the spine device will be able to figure out where is the destination leaf device by just looking into the information in the cell header. And there's no packet processing, there's no buffering. So it's very efficient. And all the Ramon spine device will switch over the cell into the destination egress leaf device. Similarly, it applies for all the other 3 flows as well. So the egress device is going to reassembly the multiple cells into an Ethernet frame and send over to the destination GPU. So basically, this is how it works. As you can see, this architecture, from the infrastructure perspective, it guarantees everything is fully load balanced. There's no hotspot in the network. So I can show you a real story. So one of our hyperscaler customer, they have been struggling. They have been struggling by all the challenges introduced by the hashing. So how they try to bypass it? Basically, instead of in their AI cluster, before any flow can be sent over to the fabric, they always send the flow information to a SDN controller. It's a centralized controller. So that controller will calculate the flow or hashing results and try to manipulate and adjust the flow information in order to load balance the flow in the potential fabric. So basically, by this way, as you can see, that's a huge latency. Every time you want to send any flow to the fabric, the first thing is to send the flow information to the controller, have the controller to do the traffic engineering and make adjustment to the flow information. Then you can send the flow to the fabric. So there's a huge delay. This is very low efficient. And also, this is not scalable. It works maybe it works when you have 10,000 flow, but it will not scalable when you have 100,000 flow. So they have been struggling about this problem for a long time. And they understand the current implementation by the SDN controller is not scalable, it's not efficient. So the moment we introduce this solution, they get very excited. So we had some POC tests with them based on the scheduled fabric. And they are just running all-to-all or reduced traffic and try to keep monitoring the statistics for every link in the network. And when they read the counter value, they observed that the utilization is very, very consistent. Every link is almost 99 to 100%. And no matter what is the mix, what's the number of flow and how big of each flow, it's always consistent. They were so impressed about the high performance of this architecture. So the moment they see the results, they get in love with this architecture. Now let's take a look at about the congestion-free operation. During the AI training, at the beginning of each iteration, so there's a highly synchronized transmission from all the endpoints sending traffic to the fabric. So in a very short period of time, the network will be saturated. So it will create a lot of transient congestion and incast. So the industry has been working very actively to innovate on all sorts of congestion-free mechanism. But with this architecture, all the complexity is handled by the hardware itself. How it works. In the similar example, the GPU A is sending traffic to GPU B, and GPU B is in the congestion status. Therefore, it sends either the pulse frame or PFC to the egress leaf device. And that moment, so when the red flow arrives the ingress leaf device, it will try to apply a credit from the egress device and tell him, I have some flow and sending over to you. Can I send that traffic to you at this moment? Because the GPU B is in congestion, so the egress leaf device is not going to send back any credits to the ingress leaf device. Therefore, the red flow will be enqueued in the view queue of the ingress leaf device. And at the same time, it has no impact about all the other flows. As you can see, all the other flows, they can flow over to the fabric without any hesitation. There's no impact because of the slow drop.
Question.
Yeah, please.
So if GPU A is wanting to send traffic, but it's gotten a halt from, or GPU B is saying I'm not ready for it, but you're saying GPU A is still sending traffic into that leaf. So what happens if that leaf's buffer gets full? What happens to those cells or frames?
Yeah, the leaf is when the leaf hit a threshold, it will start to send in pulse frame, or either pulse frame or PFC to the GPU A to slow down the GPU A.
Okay, so it can't communicate with the sending GPU to stop sending me for my buffer is full, essentially.
Right. But the beauty for this architecture is that there's no PFC propagation. So basically, instead of relying on a hop-by-hop congestion mechanism, this is really an end-to-end. So the pulse frame is, or the PFC is not going to propagate from the GPOB to the egress leaf to the spine, then go to the ingress leaf. There's no such thing happening. So all the complexity is handled by the hardware. So basically, this is only one hop congestion, just one hop. So you just need to run the PFC from the ingress leaf to the GPU-A. That is only one hop. And basically, this type of architecture excels no matter what is a workload. So the workload can be any mix of all-to-all or reduce, or scatter or gather, or any kind of percentage mix. And
question here,
yeah.
Asked. Hey, is this limited specifically to GPU workloads, or can you attach, FPGA or more specific style devices to this style of?
Yeah, great question. Actually, the endpoint can be anything. It can be GPU, it can be performance NIC or smart NIC, or FPGA, anything. So basically, it doesn't rely on the congestion mechanism from the endpoints. Everything is handled by the network itself. So the best thing about this architecture is that it just works out of box. So in case there's any change on the endpoints from endpoint A to endpoint B, and there's any link failover, or there's any change on the speed, it doesn't matter. So the network is free of tuning. So you just plug in and play. So it's a big relief on the operation and maintenance perspective.
When you say it just works out of the box, is there some established frame or format that you're using to communicate to the GPUs from the leaf switches that, like the pause frame or the go frame and so on?
Yeah, it's just a standard pause or standard PFC. That's all what you need.
I had a quick question about how you guys are actually determining the cell size and configuration. That's not Mac to Mac based. You have to use something else to hash it, right?
Yeah, that's the internal protocol. But actually, the leaf and the spine, they work together as a single gigantic switch unit. So everything facing to the endpoint is standard Ethernet. So everything inside is just the internal implementation. It's just like a chassis. You don't care what is inside the chassis, right?
No, I understand. I was just sort of curious about how you guys are actually hashing or determining what the actual payload size is for the internal portion of the fabric and what the sort of size specs are.
Yeah, so basically, when we receive the traffic and get permission to the receiver, so we will basically segment the traffic into the cell. The cell size is almost the same. And there's some kind of forwarding information attached to the cell.
Right. So it's not Mac to Mac based. It can't be, because otherwise everything would go over a single link.
Right. It's agnostic about the workload. It's also agnostic about the flow. It has no visibility about flow. It don't care number of flow or how big is the flow.
Just wants to segment it equally based off of how many paths are available from leaf to spine, right?
Yes.
Okay.
Yeah. Okay, so the moment the GPOB lifts the congestion, the egress device will be able to know, now I can send traffic to you, and the egress leaf starting to issue the credit to the ingress leaf. Therefore, the ingress leaf will start to dequeue the traffic, the red flow into the fabric and send it over. Okay, we talked about the congestion-free operation. Oops. Let's talk about the zero impact failover. So the penalty, because of network failure, will be very significant during the AI training. So as an example, in one of the Microsoft paper, they mentioned that 0.1% of packet drop may compromise the 60% throughput in the RDMA traffic. So this is very significant, very significant. So what is the behavior for this architecture? Let's take a look at. There are two aspects. Number one is about the speed you can detect, isolate, and recover any kind of failure. Number two is about the extent of the impact caused by the failure. So basically, this architecture, as I said, is purely hardware-based. It's purely hardware-based. In case there's any disconnection in the network, so the hardware will detect it and equally distribute the cells into the remaining passes. And in case there's a link recovered, it will also do the same thing to redistribute available traffic to all the active passes. So basically, the performance is very good. It's around 10 nanoseconds performance. And second is about the extent of the impact caused by the failure. So we did some kind of testing together with one of the hyperscaler customer. So in this test, so there's the x-axis, basically that is ratio, bandwidth ratio between the bandwidth to the endpoints and the bandwidth to the fabric. So we're starting from 1 to 1. That means there's no failure. And the y-axis is about the network utilization. So we are running, when we do the test, we run all-to-all or reduce traffic. And we disconnect the connectivity to the fabric one by one. So as you can see, at the moment we disconnect half of the bandwidth to the fabric, we create a 2-to-1 oversubscription. And this time, the job completion time is only impacted linearly by 50%. So this is a highly predictable and linear impact caused by the failure. And for the alternative solution, especially the example in Microsoft case, actually this is fully unlinear. So you have a small percentage of that failure, but the impact is exaggerated to a much bigger scope. This is not idle. So basically, imagine you're working in a data center with millions of servers. So basically, the interconnection in that data center will be tens of millions scale, right? So there's always link failure from time to time. So when there's a link failure, you cannot just go into the data center and replace it immediately. There's always a delay. There's always a gap. So when the network is experiencing any kind of failure, so during the meanwhile, you still expect the network to sustain in a decent utilization level. So this is a network that gives you that kind of solution. So basically, if you just have a few link failure, there's no impact. And it is still basically sustain all the efficiency for the whole network. And you can expect how much impact you will get based on the failure. It gives you a lot of time to prepare the transceiver and go to the data center to replace it.
Question.
So yeah.
Sorry. So between this with, whether it be packet loss or, latency that might be because, or that you might find in the fabric, I would think, especially since you're having to kind of do that segmentation and reassembly in the fabric, that, either you would kind of need to make sure that you have enough buffers, on the leafs to be able to handle that, or you would start to see some problems, when there were some, other issues inside of the fabric.
Yeah, so basically, the moment you get some disconnection on the fabric link, right? And so the hardware will detect it in the first time. It is very quick. It is very quick. So depends on how the failure happens. It can be managed failure or unmanaged failure. For the managed failure, we can manage to make sure there's no packet drop. Because there's always some kind of speed up. You can either make some kind of speed up on the fabric to make sure the fabric bandwidth is greater than the bandwidth to the endpoints. Therefore, there's no impact when such kind of failure. And there's also managed failure. That means so you want to do some kind of operation maintenance. So you will be able to know which portion of network you are going to shut down. Therefore, the device itself will be able to steer all the traffic to the remaining passes. So by that chance, you will not be able to experience any packet drop.
Yeah, but what about soft failures? So, so hard failures, that absolutely makes sense. But whether that just be an increased, latency or packet loss rate within the fabric.
So in the fabric, you mean for the spine layer, right?
Yeah, between the leaves and the spines.
Yeah, spine layer, actually, there's a very, very little buffer. It's almost, you can imagine as a hardwire. It's a hardwire to interconnect the different channels of the leaf device. So
I think that, I guess it's more, so the leaf is the one that's doing the segmentation reassembly, though.
Yes.
Right?
Yes.
So that's where the buffering, you would need to make sure to have the buffers to be able to support that piece of it. And I guess my question is, like, if I'm sending between, say, leaf A and leaf B, and that path, between the spines, if one of those connections has some additional latency or I'm getting some packet loss, I'm having to hold on to that, to reassemble that until I get everything.
Yeah, so basically on the egress device, leaf device, there's a small buffer to hold up and wait until all the cells has been fully delivered in order to do the reassembly. And there's a timer in case any cell is dropped. So the whole packet, there's a timeout. So they will drop out the whole packet.
Right. So is the fabric, with PFC, is it adaptable enough to be able to respond to that, whether it be packet loss or latency that's leading to those queue drops at the end?
Yeah, actually, the internal signaling is much faster than any kind of PFC or congestion mechanism. Yeah. It's much faster than that.
Okay.
Yeah.
It's not going to pass a token to receiver queue.
Yeah.
Receiver queue is not going to accept it. It doesn't make it in the fabric. Right? Because your receiver on the leaf side, right, won't make it in. So if you have congestion, it won't pass a token or anything else that it's doing to actually notify it. So the buffer will never.
Gotcha. Okay. Yeah.
Not from the spine back to. You're talking about egress from the spine back to the leaf.
From the leaf's perspective, that makes sense. Yeah.
So if they're doing it all, on the receiver side, then you're going to stop it there before it ever.
Okay.
Unless I missed something there.
Yeah.
Okay. It's quite possible.
So this architecture is very scalable. So basically, you can start this architecture from a few hundred blocks and scale out a few thousand blocks. So basically, you can build up a network with 32K 800 gig E for this. So no matter it is one box or tens of thousand blocks, it always works as a single unit. So basically, all the black box and blue box, they works as a single gigantic switch unit. So it guarantees that everything has been handled by the network itself. It always hides the complexity, and basically it's a big relief for customer. You don't need to run very complex congestion management protocol. And the beauty about that is that when you do the software development for one box, and that software will be applicable to the whole chassis as well, for the whole cluster as well. Because this is fully scalable, it works in exactly the same way, no matter it's a single unit or it is a 1,000 box. It always works in the same way. So you can apply your existing networking operating NOS system, and also you can apply the same orchestration to the cluster without any change. Okay, so basically the multi-tenants and job completion time, job isolation has become essential in the AI cloud. So the multi-tenant allows customer to share the same infrastructure, and the job isolation basically enhance the fault tolerance for the AI cluster. So what is the behavior for this architecture? So we did some kind of testing with our customer. And in this example, there are 2K GPU, and they are hosting 8 different jobs. Each job has 256 jobs associated with that. And we randomly place all the 8 jobs into the cluster and try to observe is there any dependency between different jobs. So for example, when there's no slow job, so everything works perfect. So the performance, job completion time has been normalized to 1 based on the blue bar. And we purposely create a slow job. For job number 1, we limit the receiving capacity to 70%. So by creating such kind of slow job, we can observe what is the impact and dependency between different jobs. As you can see, the result is very ideal. So only the job number 1 get impact. So the GCT is got impact by 8%, but all the other jobs, there's no impact. Yeah, so with the growing size of the AI cluster, so it makes sense that customer may want to apply the same toolkit, the same telemetry diagnostic tools from the front-end network to the back-end network. So the answer is yes. So basically, in this architecture, it enables you all sort of technologies to have the full visibility about what's going on inside the network. So for example, for the hardware, about the telemetry, that's a hardware-based S-flow. So instead of using the software to do the sampling, this is purely hardware-based. So you can sample it in a very high rate. Second is about flow latency monitor. So this architecture, actually, you may want to know what is the latency experienced for every flow in the fabric. So it allows you to monitor what is the top 8 flow experience the longest latency. And it also allows you to monitor the latency for every flow. The next feature set is called packet visibility. So basically, it allows user to find out what is PP packet processing has been conducted for every packet inside the fabric. Basically, it allows you to know what is the key, what is the lookup result, and what is action when the packet travels through the fabric. So that is what we call it packet visibility. And next one is about queue congestion monitor. So basically, this one allows customer to monitor the queue depths in real time. On top of that, it also there's another utility to enable to capture the microburst. So basically, if there's a kind of microburst and hit a threshold, predefined threshold, there will be a hardware interrupt generated to alert the management that there's a microburst has been captured. And similarly, we have very rich diagnostic tools. For example, when you build up a 32K network, there's 1,000 of walks in the network. And you must want to know what is the connectivity, what is the full topology among those boxes. So basically, every device in the leaf and the span, they maintain the reachability tables by hardware. So software can just go ahead and read the reachability table to figure out what is the real-time topology and the speed for each topology. And on top of the hardware determined load balancing, you may want to know, okay, I want to debug and check the connectivity between a certain path. By this way, you can use a source routed path. So it is more like a trace route in the IP network. So you can get the CPU to determine, to generate a packet and send that packet based on the defined path in order to verify the connectivity. So we call it a source routed path. And there's also in-band management on top of the out-of-band management. Basically, you can use data plan to send the control frame between CPU and each box. Therefore, there's kind of additional communication channels between each devices. Okay, so basically the AI is keep evolving in a very fast pace. So we need there's a change every day. There's a new model every few months. So the model, they are different on the workload basically. Some model is heavily based on auto-all, some model is heavily based on all reduce. And the duration, the scale for each model is totally different. And also the number of flow for each model is also different. So we need to have a network that is future-proof. We don't want to get a network only optimized for a specific model. So the network itself should be future-proof to be agnostic to any kind of models and get ready. So this is really the network to address such kind of request. To summarize, basically the perfect load balancing guarantees that there's no unfairness among different passes. It always guarantees the highest performance. The congestion-free operation excels in any kind of workload, in any mix. So it just relieves customer from the complex congestion algorithms. And the hardware failover make sure there's zero or minimum impact to the job completion time. And the actual high radix make sure the network can scale out as the cluster grows bigger and bigger. And this architecture makes sure that it has native support about the multi-tenancy and job isolation. So basically, Jericho3 AI is really the solution for your future AI cluster.